Well, good morning, everyone. We have a very exciting one-hour panel discussion starting now, title of which is How Technology Enables Lunar Science, Exploration, and Commerce. We have 5 panelists. They will all be speaking for roughly 5 to 10 minutes, and then we will have questions and answers. Just a reminder that please post your questions in the Q&A section. That's where we're checking for them rather than the chat window. So our first speaker today is Bill Carter, Program Manager of the NOMAD program at DARPA. For each of the 5 speakers, I try to find something unusual about them, either from their bio or by asking. And Bill has actually hiked the entire length of the Himalayas, which I think is very impressive. So over to you, Bill.
Thank you, Ben. Okay, great. So I think, Lisa, you're going to share my slides. So very much appreciate the opportunity to speak to everybody here. This is fantastic. And somehow I just lost. Okay, there we go. All right, so I have to start, unfortunately, with a caveat. The NOMAD program is in the middle of source selection, so I'm going to have to limit my comments to what we basically presented and said during the Proposers Day. Having said that, hopefully this will be interesting to this community, and I have a feeling that many of you joined us for that meeting. We had over 600 people who joined us, lots of interest, and of course an overwhelming interest when it came to getting abstracts and proposals. It's wonderful, really incredible to be engaged with this community. So let me also start out with an introduction to DARPA for the 2 or 3 of you out there who don't know DARPA. DARPA was formed over 60 years ago in the wake of Sputnik, and the intent was to develop an organization that made sure we were never surprised like that again. And that over time has kind of given rise to our current mission, which is to develop new technologies of significance to the military, to the DoD, that give us a discriminating capability over our competitors and adversaries. And then the other, of course, is that core mission to prevent technological surprise, to make sure that we never have that Sputnik moment again. So the NOMAD program very much aligns with that vision. So if we go to the next slide. Thank you. This is just a very quick overview, and in 5 minutes that we're not going to be able to cover the richness that I think the program is trying to capture. But we have multiple objectives here, and this is in terms of in-space manufacturing, lunar manufacturing, it is an enormous challenge. There are so many aspects of this, and we've tried to focus in on the pieces that we think are very important to the DoD and the pieces that uniquely enable future DoD missions, or at least make us aware of what is possible. So looking at this chart, the left-hand side is about in-space manufacturing using materials derived from Earth. The right-hand side of the chart is about manufacturing in space using materials derived primarily from the moon. On the left-hand side, we're trying to move the current thinking in the community from launch, deployment, packaging, really kind of this thought process where we develop a space asset and then it sits out there, we never touch it again, to a capability where we have capital equipment in space that can bring in feedstock, that can continuously develop and create new structures in space that are important for future DoD missions. And actually, in my little background here, you can see the canonical missions that we chose. We chose somewhere over here like solar panels, a good RF reflector, and a scalable segmented infrared telescope. Those are the canonical problems that we're asking the community to go look at and ask, when does in-space manufacturing uniquely enable capabilities in those 3 application areas? And then on the right side of the slide, it's about the moon. So can we go after those applications, the ones that are sitting behind me, but utilizing materials derived from the moon? So we're talking about high performance high precision parts derived primarily from lunar regolith or lunar derived feedstock. So that's what the program is about. And we've asked folks to push down sort of three main axes, thinking about the materials, the manufacturing, and the design. And there are a ton of other technologies, of course, that are going to be required to get us there. And I won't go over those right now. Let me just ask that we flash the next slide, which is, if the previous slide is what Nomad is about, this is what Nomad is not about. And I'll just let you read that. It's also online. You can find it on the DARPA website. If we go just quickly to the next slide, this is a summary of what we assume will be developed. And these are all technologies that we've been hearing about yesterday and we'll hear about today. A lot of assumptions here. But I am incredibly optimistic. I believe that not only this group, but also the international community is up to the challenge of solving all of these problems. So as DARPA, what we want to understand is, when do these technologies combined with high precision in-space manufacturing, materials, and design, when does that collection develop a new set of capabilities for the DoD? So with that, Ben, let me send it back to you.
Thank you very much. And then just to the audience, we will handle questions at the end. So we'll do all 5 talks first. Next is Nikkiwerkheister. She is the Director of Technology Maturation for NASA Space Tech, and she's also the LSII lead for NASA. And as I read Nikki's bio, it's, apart from being just very impressive, the one thing that I did not know was the fact she has a BA in Russian studies. So I'm interested to know more about that. So Nikki, over to you.
Hi there. Can everyone hear me okay? Sure.
Yes.
So you can. Okay, good deal.
Yeah.
Okay, good morning, everyone. I don't have any charts. I was just going to share some thoughts with you. First of all, I just wanted to say, share an interesting quote that always comes to mind when we're talking about technology development. And one of the reasons that I love so much working in this field, there's a Henry Ford quote regarding mass production of the automobile. And he said, if I'd asked people what they had wanted, they would have said faster horses. The same principle can be applied to technology development today. I think it's human nature to tend to build on what we know rather than to truly disrupt the status quo with brand new approaches. And this is one of the reasons why it was really fundamental from the very start of the Lunar Surface Innovation Initiative for us that these activities be implemented through a robust portfolio of partnerships and collaborations. I really do believe that we have to assertively leverage innovative approaches to develop these technologies. And that's going to mean really working across all of industry, big and small, new and traditional space, venture capitalists, and a broad range of stakeholders. And that is how we have established the consortium, is to do just that. So given my current role, I find it nearly impossible to really narrow this down to one technology that I feel like we need. For me, what's really imperative is that we collectively focus on developing the lunar surface capabilities over the next several years that establish what I refer to as a core infrastructure. Now, I know we've talked a lot about how to define sustainability, and infrastructure is another one of those words that needs to be defined as well. For me, the infrastructure, the core infrastructure, is what comes before sustainability. It includes the technologies that we talk about monthly in the LSIC focus groups. And these include sustainable power, in situ resource utilization, dust mitigation, access to the locations that we need to get to, excavation and construction, which we'll hear some about today from Mark and Corki, and of course, the capability to survive and operate within these extreme environments. So it's not really a matter of if it is the government, industry, academia, or international partners who are going to develop these capabilities, but how and when all of us are effectively working together in unison toward those common goals and objectives and deliberately leveraging our relative strengths to get there. So I think each of us brings something to the table, and we have to very deliberately come up with strategies and plans, just like we do for the technologies, on how we're going to work together to implement those. So for example, I believe that it's the government's role to make investments in those things that are simply not profitable for industry or academia, the pipes and roads, if you will, in order to create the foundation that they can build on, literally and figuratively. So if we're going to truly create a sustainable lunar ecosystem, I envision that the government needs to be kind of the bookends for the opportunities and funding in the beginning toward the technology development. And then we have to serve as the anchor customer on the back end as the users when these capabilities are on the lunar surface. And I think that's a really important tenet, and that's one that we need to really communicate and articulate in our strategies and our roadmaps. So fortunately, I do believe we have an approach that will work to do just this, because many of the capabilities that are required for commercial lunar sustainability are the same ones that NASA needs to enable and test on the lunar surface before we go to Mars. Now, how we implement getting there matters. So in space tech, what we've really done is we've focused a lot on developing diverse and an ever-growing array of novel public-private partnerships, collaborative opportunities, various challenges and grants, et cetera, that work with industry and academia in order to consciously balance those investments meaningfully, and then to provide that foothold and the foundation that's needed to accelerate that technology development. And you heard some of that yesterday in our opportunities panel with a lot of our different programs across space tech, everything from crowdsourcing to SBIRs to NIACs for some of our advanced concepts. So really we have kind of that large range of collaborative mechanisms across that TRL spectrum. We have multiple public-private partnerships and collaborative opportunities focused on industry developing ISRU technologies, for example. So last year we started really communicating kind of the roadmap for ISRU, but I think one thing we need to work on and talking about more is in these models, when we show these technology demonstrations and the things that we're developing, NASA is not really interested in owning or operating those technologies, but rather investing in their development so that the government can ultimately be a user of the consumables that they produce. Very similar to how the Sabatier method was implemented on space station, or where we are today with 3D printers in space. You know, there's a commercial printer in space that is owned by industry. NASA is one of the users, and we buy the prints through a services contract off of the printer. I would see ISRU, for example, operating in a very similar analogous fashion. And not only do we need to continue growing these collaborations, but we really need to ensure that we are utilizing all of these tools in the most impactful ways. So for me, that means not only communicating clearly what NASA's plans are, but then also listening to industry and academia feedback relative to common areas of interest and where the real value propositions are for our stakeholders for those public-private partnerships, and what areas that the government really needs to invest more in order to develop those roads and pipes, that primary infrastructure that will ultimately catalyze more investment in lunar sustainability. One way that we've done that is through establishing this consortium. This was not by accident, that is built into the model. It is why we wanted to, in addition to these larger biannual reviews, establish the monthly focus groups for each of the 6 lunar surface capability development areas in order to have that kind of consistent, informal, open dialogue on those key technology gaps and the needed developments for those capabilities. And so it was deliberately structured this way so that we can listen to what you need from NASA in order to really invest in and build the capabilities that you're focused on. So the feedback that we get there, that APL receives, it is integrated and it's provided back to NASA. And I find that to be really invaluable in helping us to determine how and where we need to increase our partnerships and our collaborations versus where we need to be making more internal investments to lay groundwork that's needed by the stakeholders for advanced research or facilities, subject matter expertise, and those sorts of things. Ultimately, I do believe that if we do this, coupled with the use of the upcoming uncrewed commercial lunar payload services, the CLIPS model that Joel talked about yesterday, I really do believe that we can start performing those key lunar surface demonstrations in the very near term, and those will allow us to retire the primary technology hurdles for the key capabilities at a relevant scale and buy down cost and schedule risk in order to scale them up for that truly sustainable human exploration a little bit down the road. So those are just some thoughts I wanted to share, and hopefully will prompt prompt some dialogue. So I'll turn that back over to you, Ben.
Great, thank you very much. The next speaker is Corki Clinton, who is the principal investigator of the Moon to Mars Planetary Autonomous Construction Technology, which I think is known as MMPACT. And an unusual fact I've learned about him is that apparently he has never missed an IndyCar race. Corki, how are you? Are you on okay?
Let's see. Do I need to turn on my camera, Ben?
If you think your bandwidth would handle it, that would be great. But otherwise, we can just go with audio.
Okay. Well, I'm getting a message that the host has stopped my camera. Probably a good move. So let me just go ahead with the audio so as not to. Okay, now I can start my video. There we go. Okay, Ben, I'm not sure where you got that fact, but I know you had to search pretty hard for that because it wasn't in my bio. But yeah, we're getting pumped up to go see the race again in person in a few weeks. So thank you. Hey folks, as Ben said, I want to give you just a brief introduction this morning to the MMPACT project. And as Ben said, that's Moon to Mars Planetary Autonomous Construction Technology. Could we go to the next chart, please? Okay, the goal of MMPACT is to develop and demonstrate the capabilities to construct infrastructure elements on the surface of the moon on demand using lunar regolith. The approach is that we have divided MMPACT into 3 different elements, and they're all interrelated. Olympus is the autonomous construction hardware system development. Microwave structure construction capabilities is focusing on specifically being able to develop structures using microwave centering. And then the construction feedstock materials development supports both microwave and also Olympus. And I will mention that we've used a variety of procurement and collaboration mechanisms, from SBIRs to cooperative agreements to competitive solicitation. And we have over 25 partners that are helping us that range from large business, small business, other government agencies, other NASA centers, academia, across the spectrum of organizations are involved in bringing their capabilities to help us solve this really challenging problem. And some of these challenges are listed below. And these are just a few of the high-level gaps. Obviously, we have to be able to find a material and a process that will work in the lunar environment and that will stand up to the lunar environment. We also hope to increase the autonomy of operations of these, tending toward as full of an autonomous process that we can achieve. We have to be able to solve the extreme challenges that the lunar environment presents to us. We have to be able to have machines that will operate in that environment, not just the temperature extremes, but the lunar dust. And we also have to have power. So long-term operation is a key. And then we have to understand how we can scale up from the very elementary beginnings, the proof of concept that I'll talk about later, all the way up to creating functional infrastructure on the surface of the moon. Could we go to the next chart, please? I just mentioned some of those challenges, some of those gaps. This is just a graphic to explain how much impact depends on other elements, on the success of other elements within LSII. Obviously, as I'm talking, we are developing the construction capability, but we're going to need power. We're going to need to interface with the excavators that will do both site preparation and also gather and size sort the regolith for our production capabilities. We're going to have to rely on communication and navigation. We're going to have to rely on dust mitigation strategies that are being developed by other projects. So, and these are not all. Obviously, we're working with Mark, that you'll hear from a little bit later on, to refine these gaps and also to reach out to the other projects and make these connections. So the message here is it takes a village of capabilities to create a village on the lunar surface. Could we have the next chart, please? Okay, our first demonstration mission on the surface of the moon, and we're targeting the 2026 timeframe, will be to demonstrate viable ISRU-based structural capabilities. And this is both the materials that we will down select and the associated process that we will down select. We want to be able to live off the land, much as the early pioneers and the early explorers did. We want to minimize the upmass that we have to launch and carry to the moon. And we want to show that we can operate and work successfully in the very challenging lunar environment. The other thing that we'll have to learn, which I'm going to talk about in the next chart, is how do we scale up to create functional structures on the lunar surface? And let's talk about that on the next chart, please. Okay, on the left-hand side, we're going to talk about phase one. We're currently in phase one, and then we're going to move through the phases that we envision leading to a lunar settlement. Right now, we're developing the materials and the processes, and we're evaluating multiple materials and processes, as I said earlier. The excavation team is also working on the excavation capabilities, and together we are working towards how we interface and talk. What are the sizes of the regolith that we need? How are we going to convey it from what they've gathered to get into the system so we can place it right where we need it for the production environment? In the next, down in the lower left, middle, is our vision of that first demonstrator on the moon. Again, this is just a proof of concept. We want to show that the materials and the processes and the hardware will work. We want to demonstrate both vertical structures, knitting additively constructed materials together to form a vertical structure, and horizontally, showing that we can make a planar structure. The vertical structures, obviously, we're talking about things like habitats and shelters that will protect the astronauts from the lunar environment and the equipment from the lunar environment. And the planar structures are things like roads and landing pads that will help to reduce dust in the environment and will also improve the trafficability as we move to greater and greater habitization of the moon. Okay, now let's talk about phase two. Phase two is shown in the lower center of the chart, and that's where we're progressing to actually produce functional infrastructure on the surface of the moon. You can see there we've chosen to demonstrate a landing pad as a planar structure, obvious use there. And then on the right-hand side, an architectural concept for a lunar habitat. Those demonstrate the planar, horizontal structures and the vertical capabilities. As we move forward into phase three, we're looking toward constructing what we're calling the lunar outpost. And in the upper right, you can see an overhead view of what that outpost might look like. The torus-shaped structure there is a habitat. You can see one that's completed, one that's being built in the lower right. What you can't see that are off this graphic, on the outside on the right is it's a solar farm, and on the outside on the left is a greenhouse. So that is what we're calling the lunar outpost. And back down to the lightly colored shaded blue circle, you can see astronauts there living and working inside that torus-shaped structure. And then finally, as we move to phase four, we're calling that the lunar settlement. That supports the sustained presence on the lunar surface and helps to enable a lunar economy. So that is the backdrop that we're showing for this entire slide. That's our vision. It's a very exciting project. We're very happy to be working with Niki and LSII and also Mark Hillburger as we go forward to identify these challenges and make connections to the capabilities that are out there to help us solve these challenges so that we can achieve this vision. And that's it. Thank you very much.
Great. No, thank you. And our next panelist is Sandy Magnus, who's currently the principal of AstroPlanetview. She's had a very impressive career, obviously, including flying in space. And the unusual fact for her was the fact that I don't know if many of you have seen the candy corn matrix experiment that was conducted, but she was actually a witness to that, and you can find that on YouTube. And she was involved in the very high-tech cleanup, which involved eating the candy corn. Over to you.
Thank you for that. And that was a lot of candy corn, and I couldn't let Don Pettit get himself sick eating the whole bag himself after doing that really spectacular experiment. I'm going to approach this question a little bit differently than everyone else. I'm going to put my operator hat on and talk about the technology from that viewpoint and draw a little bit further down a layer from where Nikki was talking about the role of LSIC, and I'm going to talk about this idea of infrastructure and standards. You know, on space station, when I was up there, it was clear that we hadn't really thought ahead of time to the extent that maybe we could have on standardization for different parts of the station. We had for example, we had three different colored power transformers that we needed to use based on the equipment. We had a white brick, a blue brick, and a green brick, and those were all different: 120 volt to 28 volt, 28 volt to 10 volt, 120 to 10. I mean, it was just wacky trying to manage that. And as all of you start thinking about the technology that you're going to build for the moon, I would really encourage you to think about how the technology is going to be used and operated and maintained. And some of the groups discussed this a little bit tangentially yesterday. It's not too early to start thinking about those things. And there's efforts I see happening along these lines, but I haven't yet seen where it's all getting pulled together. You know, for example, I'll go back to the word infrastructure. Everyone's using that word in different ways, just like everyone's view of the moon and how we're going to use it is different. And that was mentioned yesterday as well. I'm pretty sure somewhere at NASA, there's a list explicitly of infrastructure, and I'm hoping that it's prioritized in the way that NASA feels it's important to tackle. But I wonder if the LSIC community has come together yet to create their list of infrastructure that they think is important for what their goals on the moon will be pre and post, you know, NASA engagement at any level. And from that list, do you guys all agree with what you think is important? And have you compared that list to NASA's list to find out where the intersections are? You know, for example, comm came up yesterday. You know, what kind of communication infrastructure does industry need? You know, what do you need roads? Do you care about roads? Do you care about the power system? Do you care about what the power system is? We settled on 120 volts for space station. I don't know why, that was before my time, but that created some problems in some areas. And so I would encourage the LSIC community to figure out how to come up with your list of infrastructure that you care about and then share that with NASA. And in the context of doing that, you'll also be able to figure out, as an LSIC community that is interested in doing things on the moon that might be different than what NASA's long-term plans are, what are the standards or the interoperability systems that need to be baked in from the beginning. For example, I'm hearing a lot about autonomous construction on the moon and robots running around doing different things. What do the interfaces look like between all of these robots so that they can work together? We have one grappling well, more than one now with the SPDM, but we've got one or two grappling mechanisms on the space station. And it's likely that on the moon we'll need a couple of different kinds of interfaces, but yet where is that conversation happening, and how is industry providing their input to NASA? Because I've heard that HEOS is working on some interoperability standards, but I'm not entirely sure who they're working with from this group or what industry partners they're coordinating with to figure out how industry can provide that input. And this group, I think, is the pathway, to Nikki's point, to providing some of those inputs. So what do you care about from an industry viewpoint? Again, thinking about yourselves as the operators and how you can bake into the technology, you know, the kinds of things that you need to operate much more easily. I mean, down in the weeds as well, hatches. You know, there probably should be one standard hatch design that everybody is using. You know, that's again in the detail, but these are the kind of things I would encourage you to think about. There was some discussion yesterday about modular open system design. That's certainly the way to go. But again, you know, the next layer down is what are those specific elements that we know we need to have modular and open, and start defining that now. Otherwise, as the technology starts to get developed, if you're not thinking about this endpoint at the very beginning, it'll be hard to go back and bake that in at the level that you need in the design phases and the formulation phases to have a nice, interchangeable, usable, you know, minimal logistics even system. So I would just offer those comments for your consideration. And in the LSEC community, again, identify what you mean by infrastructure and prioritize it, and make sure you share that with NASA, because they have their lists and you want to make sure you get your input in. So I'll stop there and be happy to answer any questions that anybody has. Over.
No, great, thank you. That was excellent. Not least because you've helped me think of a couple of good panel questions for the end. And our last panelist is Mark Hillburger, who's the Principal Technologist for Structured Materials and Nanotechnology for NASA STMD. And he builds and races, or used to build and race, classic sports cars. But also, when I looked in his bio, he did modeling of buckling of critical launch structures, which I have to admit is something I had never thought of. Over to you, Mark. Mark, can you hear us? We cannot hear you if you are talking. Okay, Mark, one more time. If not, we'll perhaps jump into a question and come back to your talk when you make it on.
Looks like he's unmuted now.
Okay. Mark, are you with us? Okay, I'll tell you what, if the other panelists could turn on your cameras, I'd like to start with, I'll start with a question, and then if Mark comes back on, we can certainly happy to listen to his talk. Okay. Other speakers, are you able to hear me?
Yeah.
Ben, this is Sandy. I hear you.
Great. If you could put your video on, that would be great for the question. So, so the first, there was to follow on the idea of standards. Standards can be a double-edged sword in that they can help, but also they can hinder innovation. If the government forces a standard that a company, if you're trying to have competition between companies and those companies have different standards. So I wonder if the panelists have any thoughts on, clearly there are benefits to standards, but how do you avoid some of the pitfalls of the government enforcing a standard that ends up not helping?
If I may, I think the key is for industry to be this group, if this is the right group, be proactive about what standards or they feel would be helpful, and they prioritize and focus on those, right? And that way industry has an input about what is being propagated, as opposed to waiting for NASA to issue some. I think there's probably going to be a whole conversation about safety that's a little bit more thorny, but from an interoperability or an interface viewpoint, I think if industry has takes a proactive stance here, you can certainly minimize the amount of random standards that get set that aren't maybe necessarily important to everybody working together. Over.
Hey, I'm back. Can you guys hear me? I'm sorry.
Yes.
As soon as I hit unmute, my Firefox took a dive.
Okay. So Mark, we're just starting a question. What I'd like, if we can we'll finish this one question if we may, and then we'd love to hear your talk.
Oh, absolutely. Yeah.
So, do any of the panelists have anything else they want to add on the, how do you make sure that that doing standards is good?
Go ahead, Corki.
I'll add a comment on that, Ben. I didn't talk about it, but on my slides, I had as one of the capability gaps or a challenge is the lack of standards and requirements for construction on the moon. I mean, we're going to be using an unusual process, no matter what it turns out to be, and an unusual material, and one in which it will be difficult to get, let's call it, statistically significant design properties. And depending on what we build, we are building things that will be used by humans. So we need to make sure that those structures, be it a landing pad or a habitat, are safe for human use. So that is a challenge, and we're going to need those standards to help us when we design, and also to understand how much testing we're going to need to do on these materials. So that's a clear area where we need the community to help, and that's architects, it's NASA, it's industry, it's all those people that Sandy mentioned. That's all.
I'll just amplify it really quick. Standards are I think best developed with all the stakeholders involved. And if you look at how the IEEE does things, or other international organizations, you have to have all the stakeholders up front working with you. I think the key in this case is understanding who those stakeholders are, and many of them probably don't exist yet. So it's interesting. It's an interesting conversation.
Mm-hmm.
Thank you.
Yeah, can I just add to what Corki said? And I didn't catch the whole question, but I think I understand what the question was. Yeah, so getting standards like what we would use terrestrially, but also I think there's a lot of unknowns in terms of what are we building on? How are we going to understand, say, the density of the regolith, and when we go to build a foundation, how do we verify the quality of the foundation that we're going to build from? So a lot of unknowns in terms of what's there, not only materially and the types of materials that we can use for construction, but also the understanding what the surface is like. How do we design for things like moonquakes and that sort of thing? So many different unknowns that need to be characterized before we even start laying the first brick on the moon, for lack of better saying.
Thank you. So, Mark, would like you to have a chance to give your presentation now, please.
Sure. Yeah, I only had one chart, and this is where things went south. So maybe if somebody had charts they can put up for me, that would be great. Yeah. So I'm a principal technologist for structures, materials, and nanotechnology, although I don't do a lot in the nanotechnology area right now. And basically, just to give you an understanding of what us principal technologists do, STMD has a series of principal technologists across several technology disciplines, as well as system capability leads for various disciplines. All told, there's probably about 13 of us. But one of our primary functions is to assess technology needs and provide guidance on how, what technologies we invest in, and in coordination with all the NASA programs and missions, develop investment strategies and plans. We're coordinating with other disciplines, and as Nikki was saying earlier, and Corki, for example, in the area of lunar surface construction, there's a tremendous number of dependencies for for excavation and construction. And I do a lot of coordinating across, for example, surface power, ISRU, extreme environments, dust mitigation, and advanced manufacturing, for example. So we're very busy right now. It's a really exciting time, not only the mission, but also the opportunity to work across all these disciplines. It's extremely, extremely important to make sure that we're thinking about all of our dependencies as well as our stakeholders as we put some of these plans together. And so this one and only slide that I have here is just to give you an idea of the type of work that I am currently doing. We're all of us PTs, principal technologists and system capability leads are on task to develop a comprehensive set of roadmaps and technology gaps that we can use to help guide these technology investments. And my biggest area of emphasis is on autonomous excavation, construction, outfitting. I have a lot of other roadmaps associated with other areas, including nuclear power and just a tremendous variety of applications for structures and materials, as you might imagine. But of all of them, autonomous excavation and construction rise to the top. I've also included outfitting. That's something that until recently hasn't received as much attention. And when we talk about outfitting, we're talking about how do we integrate the various systems like power, data, and ECLS into these structures as we're building them. So I always use the analogy of when you're building a house, the first thing you do is you put up, sort of the primary structure, but then you have to come back in and pull wire, cable, all your plumbing and that sort of thing. How are we going to do that? And it also gets to the point that Sandy made earlier about standards, standardization of interfaces, and that sort of thing. And those are some of the conversations that we are currently having, and we need to continue to have. And I think LSIC is a great opportunity for us to engage and understand options on how we might do that. Let's see, just going down the list here. So we are definitely working towards a permanent sustainable lunar settlement like the one that Corki has shown. And so obviously there's a lot of work that has to be done there. And so I've broken out just some 4 very basic technology focus areas. 1, construction, materials production, utilizing in situ resources. Again, coming up with the materials, the processes. We're going to have to be able to build or construct construction agents, autonomous construction agents that can survive very long duration operations on the moon. So for example, excavators that are going to be excavating lunar regolith to provide not only feedstock for ice mining and regolith extraction of materials such as water or other minerals. We're talking about excavation of hundreds or thousands of metric tons of regolith. So these machines have to be able to operate for long durations, multiple lunar days and nights. And so we have to worry about everything involved in surviving those lunar nights, but also the abrasive nature of the regolith and the fact that these excavators, like for example, the one that's in the upper right image in the slide, they're constantly digging into that stuff. So understanding how the implements are going to be wearing over time, dust infiltration into joints, dust covering heat rejection radiators, and how do the radiators perform over time. Just a incredible number of things that have to be dealt with there. Landing pad construction is a huge area of emphasis. We're starting out small, like Corki was saying earlier, but very quickly need to grow to human lander scale landing pads. Unpressurized structure scaling up to single and multi-level pressurized habitats. So how do we go from building horizontal structure like landing pads and roads to vertical construction? And then finally, as I mentioned earlier, outfitting these structures for data power and ECLS, for example. And I could have gone on many slides discussing in more detail the plans associated with this. So it was either this one slide at a real top level or 20 slides. So I stuck with the one slide. But it's very exciting, and I'm happy to be involved, and I kind of fit in between Niki and Corki in that I'm trying to provide the technologies that Niki and others need up at the mission level, and pull on people like Corki and folks that are involved in other projects that are actually doing the real work down in the trenches and making these technologies come alive. So I'll end there, and I thank you for the opportunity.
No, thank you very much. So just in the questions and answers, several of the questions are aimed at individual speakers, and I'm going to try and use the remaining time to ask more general questions to promote discussion. But if you see a question that's aimed at you, I'm sure the questioner would very much appreciate an answer. I'm going to merge a question that we got with one that I was intending to ask. The question that's been asked is, we just celebrated 20 years in Earth orbit on ISS. What do we think realistic lunar scenario is 20 years from now? And as you talk about that, the question I wanted to kind of feed you is, in order for what you think that should be to come to pass, what is the most important either new technology or new data set? What has to happen over the next 5 years, do you think, in order to make what your vision is for 20 years time come to fruition? And I will let whoever wants to go first, but no one will escape.
Okay, I'll go first. We need the appropriate budget.
Yeah.
It's not technology, but we've got a budget.
I'm thinking of the Star Trek quote, isn't it, from Bones? I'm a doctor, not a magician, or something like that, right?
I'll tag on to Sandy's comment, and it's having the budget to have lunar access. As we've talked this morning, there's a lot of things that need to happen on the moon to accomplish that village. And in order to demonstrate that we're moving forward to accomplish that goal, we have to have access to the lunar surface. A lot.
Yeah, and Ben, I'll follow up on that a little bit, I guess. I don't want to interrupt. So I want to go back to what we talked about with infrastructure a little bit, right? And those to me are what I consider to be what I would call the precursor to sustainability. And that really does start now with the early lunar opportunity. So for example, there's a basic amount of power that is going to be needed, right, to explore and operate on the lunar surface. And of course, those needs are going to grow over time as we progress from robotic to human missions. So while we may need 40 kilowatts for human missions, maybe on earlier robotic missions, we may only need 1 kilowatt or 3 kilowatts. But the same principle can really apply across all other categories that we've talked about, 5 other categories. For ISRU, we have to test the basic processes on the subsystems and on scale demos in that relevant lunar environment before folks are going to invest in a full-scale production system. So, and Corki touched on the same process for initial construction demonstrations. So to me, the reality is that getting to sustainable capabilities on the surface requires a phased approach. The one thing that I do know is that there will be lessons learned from the early lunar demonstrations, and those include lessons from the known unknowns and unknown unknowns that are out there. So part of the challenge for me, and I guess the fun too of the technology development, is how to plan how we do this and how to incorporate the lessons into those scaled up systems that build on this. But we do have to start that now, and that means for me taking advantage of every single early CLIPS mission available to do that. And to do that, it means we have to have a plan. So yesterday, for example, Jim Ryder showed a slide that had think we have up to 30 something, don't quote me on that, planned early lunar demonstrations on the CLIPS mission. That was on one of his charts. And what those specific demos end up being and testing requires dialogue, strategy, and resources across this whole community. So I really view those early robotic missions as necessary opportunities that we have to leverage in an organized fashion to test out a variety of technologies and approaches. And I really believe that we're literally on the cusp of evolving the technology development from the philosophical to the fruition phase. But I think we have to have that plan and, like Sandy said, the resources. And that's why this whole LSIC forum for us is not kind of a philosophical forum. It's very cathartic, right, to get together and talk about what we envision. But these focus group meetings and having folks like Mark Hillburger, who's the principal technologist, as he mentioned, for that area, he is the NASA POC for the excavation and construction group. So we have that across all the groups where those NASA principal technologists and system capability leads are the NASA focals working with the APL counterparts so that the feedback that we're getting there and those dialogues are being integrated into those technology assessments. So I would just say that I think we're in the phase, we've got to start looking at this as an execution phase and really leveraging those early lunar opportunities like others mentioned. And that means having the resources to do that, as Sandy mentioned.
Thank you. Bill?
If I could build on what Nikki was just saying, in developing these roadmaps, we, the autonomous excavation construction outfitting roadmap that I'm leading, we've got a really great team of experts, both in excavation and construction, with folks like Corki and all. And so the plan and identifying the gaps really is coming together well. And I'm really excited to be engaged with LSIC and various working groups, because as I mentioned earlier, there are a lot of dependencies, and so, for example, power, extreme environments, dust mitigation, as well as the excavation and construction working groups, all are helping me further define and refine the plan. And so I just wanted to say that it's a great opportunity for us, as well as developing better relationships outside with industry and academia. And we need to make sure that we're taking full advantage of that opportunity as well. As far as the challenges that I'm seeing as we're working through these roadmaps, and I kind of alluded to it earlier, are really the unknowns associated with not only what we have on the lunar surface to work with, but other issues associated with specific missions. And for example, landing. What are the landing loads that we need to be designing landing pads to? There's both, the thermal, there's pressure. How big do the landing pads have to be? So what precision are our landers going to be able to land with? Until we start getting answers to those questions, we're sort of having to cast a much wider net in terms of what technologies and presuming very large and heavy duty landing pads, but that might not be the case. And until we get that information, I think a lot of our trades will remain sort of in limbo until we get that sort of information.
Okay, thank you. Bill.
Okay, last but not least, hopefully. So I think, we've come to the conclusion that there's no one tall pole in the tent. There's a lot of tall poles, and it's a pretty big tent. So, but I'm optimistic that over time, with the right, focus and the right funding, we're going to overcome all those technical hurdles. I think one thing that could be critical to helping us make sure that the stakeholders who, we're asking that money from, we keep them happy, would be a better way to estimate cost. Having cost models which can underpin the proposals that we put forward for how we're going to go accomplish these goals would be immensely helpful. Much of my job would be done if I had good cost models that I could rely on. And so I think a lot of these early studies are going to pave the way for making at least believable cost models. But we need to think about that.
Okay, thank you. So I want to try and sneak in one more question, which is, we had a discussion on infrastructure and, the usual suspect, your power com, which obviously we all agree on, but I wonder if anyone panelists could comment on how do you decide when the government does something versus, say, the government saying, hey, we'll just buy the product and we'll do an RFP and someone produces it. So we all agree we need the key infrastructure in place. Maybe people can comment on experience or thoughts on the challenge on how to do the implementation, how to do the execution, because there are different ways of doing it. And I will let Bill go first because he ended up going last.
Good question. Well, DARPA's role is trying to knock down that initial really tall barrier. So I think in many cases, you may need the government to do it for the first time. Even if we do it badly and everybody else goes, hey, wait a minute, they're going to pay us to do that and we can do it so much better and our margin will be, this much. I think that would be immensely helpful. So that's a partial answer.
Thank you. Yeah, no, it is. Good partial. Anyone else?
Yeah, I'll just say I think I answered that probably in my first one, where I just feel like it's really the government's job to do those things that aren't profitable for industry. So a lot of laying those pipes and roads and listening to what industry is needing to enable them. And I guess like going back to what I said about being the bookend, the government has to make those investments, which, quite frankly, I always laugh and say that, I tell my mom I always wanted to work for NASA. I never thought I'd get excited about acquisition mechanisms and contracts, and but I do, because those are realistic ways to work together and with more agility and flexibility. We have to have a variety of acquisition models and procurement mechanisms, like the tipping point, where again NASA doesn't own or operate those capabilities. We're wanting to invest in industry who is developing those so that we can be one of the users and really implement that bookend model. But that means we have to be able to hear from industry and get that feedback on where they're making those investments and where their interests are as well, if we're going to grow public-private partnerships. So yeah, that's my thoughts.
If I can add to that, one other factor here, I think that we need to keep in mind is, NASA's going to the moon in order to be able to go to Mars someday as well. And as the government thinks about what they should invest in and what industry should develop, I think there's a factor here, not only to Nikki's point about what can government do that industry cannot because there's no profit in it, but I would also say a strategic look at what technologies need to be developed that once they are developed are available to disseminate throughout all of industry so they can keep innovating on, versus if you have a specific company developing a specific widget, that company owns that IP and that information is not spreadable to everybody else, right? So as we go to the moon, everyone in industry is successful because of 50 years of government investment in technology that everybody is available to use. And so what is that leading edge of technology that the government needs to make sure that they maintain the intellectual property on, so they can spread it out for the next 50 years of innovation to leverage. So I think there's a factor that the government should look at there as well, besides just the point that Nikki made. Over.
Great, thank you. Well, I'd like to, we've come to the end of our time. I'd just like to thank all the panelists again. I think it's been excellent conversation, and thank you all for your time and energy.